Good day. In this video, I will talk about bosonic systems, in particular, how to do calculations in first quantization. I should emphasize that there is a technique, second quantization, which was invented to make these calculations easier. So, and that's how usually they're done. But if you want to prove the equivalence between first quantization and second quantization, these are the types of calculations you need. So these are more sort of auxiliary exercises for a many-body physics uh, study. Okay, so let's first look at um, a simple system. Okay, so we have three particles, let's say. So three particles. Okay, and they are bosons. Okay, and we're going to say that um, these particles are in two states. Okay, so two particles in state one and one in state two. Okay, and we have to write the wave function for this. But what we have to, so obviously we're going to have a wave function. Let's denote that psi as r1, r2, and r3 because we have three particles. But this wave function has to obey the following condition, that if you exchange any two sets of coordinates, you get the same thing. Okay, so for example, you should be that wave function should be equal to r2, r1, r3. But if you switch 3 and 2, you should also get this. Okay, so this should also be equal to psi r1, r3, r2. Okay, so these conditions should be satisfied for any pair. Any two-particle exchange should lead to the same wave function. Okay, and now state 1, okay, is going to be a function phi 1 r. That's state 1. And state 2 is another coordinate-dependent function phi 2r. Okay, and we're going to assume orthonormality. Okay, so this is a complete orthonormal set. So that means that the following is true. Phi I, and we're always going to assume this for this video, phi j r, you have to put an asterisk, and d3r is equal to a Kronecker delta. Okay, and I want to write the wave function for this system so that the symmetry condition that I specified, and this is the bosonic symmetry condition that I wrote here and here, that those conditions are satisfied. That set of conditions, one might say. And one can sort of do this easily just by looking at it, right? So we have psi, and let me make a simplification. Okay, so before I write this, let me write this notational simplification. I'm not going to write r1, r2, and so forth. I'm going to write just the number 1 and 2 in this case. Okay, so for example, phi 1 r1, I'm going to write as phi 1, 1. This is actually a notational simplification, which I actually lifted from a quantum chemistry book. Okay, so let's try to write the wave function, because I'm going to now write psi 1, 2, 3. It's much easier to write it this way. And well, you know that it has to be a product function of the orbitals. Okay, but if I just write a simple product, let's say particle 1 in state 1, particle 2 in state 1, and particle 3 in state 2, well, that certainly satisfies the definition of our wave function. but it doesn't satisfy the symmetry condition, right? So these are bosons. The wave function has to be symmetric, okay? But what you can do is symmetrize it by adding the following terms: phi 1, 1, phi 2, 2, phi 1, 3. Okay, and the third term, which is phi, sorry, that's a mistake. Phi, that should have been a 2. Okay, so phi 2, 1, phi 1, 2, and phi 1, 3. The only problem with this wave function now, so this satisfies the condition. If I switch, for example, 1 and 2, in this wave function, if I switch 1 with 2, nothing changes, right? Because these are phi 1, phi 1. Okay. In this, if I switch 1 and 2, these two exchange, okay? But then this part of the wave function becomes this one. And when I exchange here 2 and 1, the opposite happens. Okay, so this wave function now obeys the symmetry condition. But one thing that's not obeyed is that this is not a normalized wave function. Okay, and what do we mean by normalization? By normalization, we mean that the triple integral of all three coordinates psi 1, 2, 3 squared is going to be has to be equal to 1. Okay, well, let me actually multiply this by a normalization constant, some real number, and this has to be 1, and we are after determining n. Okay, so we do need to do this. And so this is actually, okay, we see that a psi has 3 terms. Okay, so this is psi. This is squared here. Okay, so modulus squared. We have a modulus squared here. So a psi has 3 terms, which means that this psi squared will have 9 terms. And of those 9 terms, 3 are like multiplying like, and 6, the remaining 6 are, let's call them cross terms. Okay, so what is a typical like part multiplying like term? That's going to be integral, so triple integral. There, the dot should not be there. No, the integral should be there, but the dot should not. Okay, so d1, d2. So I'm just going to quickly normalize this. d3. And there's going to be one term, which is phi 1, 1 star, phi 1, 2 star, and phi 2, 3 star. That's a 1 there, sorry. Phi 1, 1, phi 1, 2, phi 2, 3. Okay, so that's one term that you're going to get when you take this wave function here. So this is your full wave function, and you take this and you substitute it in here, and you square it. So this times itself is precisely this term, but this can be written as a product of, for example, this integral, okay, then a product of this integral, so that's a 1. So now I'm doing d2, this one, and this one. Okay, and this is still multiplied by the terms having to do with 3, which are d3, phi 2 star, 3, phi 2, 3. Okay, and these are all 1 because the wave function is normalized, so you get a 1. Okay, now what else can happen? When you square this wave function in order to substitute in here, you also get cross terms. For example, you would get this term multiplied by this term. Okay, so you would get that. Let's see what happens in that case. So in that case, you have triple integral d1, d2, d3, phi1 star 1, phi1 with the second particle in state 2, and that's also asterisk. Let me finish this phi, sorry. And phi 2, third particle. Okay, so that's, let's say, the bra side, if you're familiar with Dirac notation. So this, and let's multiply it with this from the other side. Phi 1, 1, phi 2, 2, phi 1, 3. Let's see what happens. Okay, so phi 1, 1. Let's put the 1 there. Phi 2, 2. And phi 1, 3. Okay, and that's still a three-particle triple integral. And if we work that out in detail, I can get rid of that dot. Okay, whatever. Let's. Okay, if we work this out, then we have d1 is phi 1 star phi 1. That's just 1. Okay, star 1 phi 1 1. But for the other two, so the integral over d2, you're going to get phi 1 star 2 and phi 2 2. And we said that these are orthogonal functions, so this actually gives us a 0. We don't have to work any further. So we get 0 out of the cross terms. Okay, so like terms give us a 1, and cross terms give us a 0. Okay, and if you do all these integrals, you see that since there are three like terms, when you do this integral, you get 3, because it's 3 times 1. In other words, the normalization constant is n squared times 3 equals 1, meaning that the normalization constant is 1 divided by the square root of 3. Okay, so your overall wave function, you need the normalization constant in front of it. That's your overall wave function. Okay, so now we did this. Let's analyze this wave function a little bit. Okay, so here's our wave function with its 3 terms and 1 divided by square root of 3. This is a wave function over permutations, okay, but only over distinct permutations. In other words, if we permute 1 and 2 in this term, nothing happens, okay? So we only have distinct permutations. If you considered all permutations of the indices 1, 2, and 3, coordinate indices, you would have more than 3, right? And the reason is because, well, you would have 3 factorial permutations in that case, which makes 6. Okay, but 2 of your particles are in state 1, so this needs to be divided by 2 factorial. And one of those particles is in state 2. Okay, so it also needs to be divided by 1 factorial. And so in the end, this summation is over distinct permutations. So for example, what doesn't appear in this summation is the phi 1, 2, phi 1, 1, phi 2, 3. Okay, because this is the same as this one. Okay, so that doesn't appear as a distinct term. That's what you would get if you permuted. So you just wrote 1, 1, 2 and permuted 3, 2, 1 according to all its 6 permutations. More generally, we can consider a wave function. Okay, so let's consider a wave function in which we have n particles. And of these particles, n1 is in state 1, n2 in state 2, and I don't know, we'll just say so forth. Okay, so this is a general wave function. And I just want to finish off by writing the general form for such a wave function. Okay, So, and maybe what I also do is normalize it. Okay, so I have my psi, okay, and my psi is 1, 2, etc. n, and it's going to have a normalization constant, which is going to be the square root of n1 factorial, n2 factorial, etc. And that's divided by n factorial. Okay, and so that's going to be the normalization constant. That's a 2. I'm trying to make that a 2. I'm not, maybe I'm not too successful. Let me make a better 2. Okay, now, but I haven't given you the function yet. And the way I'm going to write it is sum over p. And okay, we'll just, actually, I need more space. Well, I think I have space. No, I don't. Sorry. I'm going to erase this. And since I need more space, I'm going to write it here. I'll just put a multiplication sign and I'll continue the expression here. Okay, and what I'm going to write here is sum over p, which is the sum over permutations. And I have phi1, p1, phi2, p2. No, not phi2, sorry. Phi1 still. I mean, it could be phi2 if you only have one particle in state 1. Okay, the point here is that you have n1 particles in state 1. And at some point, you will have to start listing your phi2 particles. Okay, and I could write that as p n1 plus 1 here, right? Because the first n1 are in state 1 and up to p n1 plus n2, you have the particles in state 2, and it keeps going like this. Okay, so you always have n1 particles in state 1, n2. So this here starts at n1 plus 1 and goes up to n1 plus n2. That way, you always have n2 products of the phi2 wave function, phi2 orbital, you might say, a single particle wave function next to it. Okay? Now, okay, and I'm going to close this because there was a sum there. Okay, and what is this sum? We have to talk about that. And this sum is over all the distinct permutations of coordinates. Okay, so you can relate this to our 3-particle example because I said it's not all permutations that appear, only the distinct ones. Okay, and so we have to make that different distinction. Okay, so here you have, let me actually make this clear by using the 3-particle wave function, what I mean by the sum over distinct permutations. But let me write this, just make a note of it, that the sum over p is sum over distinct particle coordinate permutations. Okay, so sum over distinct coordinate permutations. That's what this sum here refers to. That particular sum there refers to. Okay, and let me just show you how you can. Okay, so for example, if you have a bosonic system, you could start like this. Okay, so first of all, for a bosonic system, you can represent the wave function by a permanent. Okay, so typically you would have a set of particle indices, but I'm going to do this for three particles as an example. Okay, so if I have three particles, my permanent is almost like a determinant. Okay, so I don't really know what the notation for permanent is, but I'll just improvise one. Okay, so I could write the following. I have a matrix, and I'm going to give the particles indices alpha 1, coordinate 1, phi alpha 2, coordinate 1, phi alpha 3, coordinate 3. Okay, and then I would have here alpha 1, coordinate 2, alpha 2, coordinate 2, and alpha 3, coordinate 3. No, sorry, that's a mistake. What did I make a mistake? 1, 2, 3. No, sorry. Let me fix this. Okay, that's a mistake. So this should be 1, and this should be 2, 2, 2. And I'll explain the pattern in 1 second. Apologies. And here I have phi alpha 1, 3, phi alpha 2, 3, phi alpha 3, 3. Okay, that's a matrix, okay, of functions. And you have okay, alpha 1, alpha 2, alpha 3. The orbital indices are increasing this way. The coordinates of the particles increase this way. That's how you construct this matrix. And what a permanent means is that you basically, it's like calculating the determinant, but everywhere you see a minus sign, you make it a plus sign. Okay, and this actually will give you n factorial, that is 3 factorial terms. So it will give you 6 terms. But you will, if you have indices, or orbital indices, or state indices, which are identical, then some of those will be redundant. Okay, and let's take the example that we had before. So let's say alpha 1 is equal to alpha 2 equals 1. Okay, so two particles in state 1, and let's put the third particle in state 2, and let's see what happens. Okay, so if you take the determinant, but then you actually make everything a plus sign in the end. Okay, so I'm going to take this determinant, but I will keep on make all minus signs plus. Okay, so I guess I'll start here. Okay, and I will have phi alpha 1, 1, phi alpha 2. Oh, sorry, but I want to use the state indices that I specified. Okay, so it's going to be phi 1, phi 1, 2, phi 2, 3. Okay, so that's this one times this one times this one, and I'm going to have my second term is going to be phi 1, 1, phi 2, 2, and phi 1, 3. Okay, so this is the phi 1, 3, this is the phi 2, 2. Let's keep going. If I go up here, I have alpha 2 is 1, so again I have a phi 1, 1, right? Phi 1, 1. Here I have a phi 1, 2, phi 1, 2, multiplied by phi 2, 3, phi 2, 3. But notice this term is the same as this term. Okay, so this is going to be, in this sense, redundant. Okay, and then you keep going and figure out the other terms, just like you would in an ordinary determinant. Let me just finish that for completeness. So I have phi, what do I have? Phi 1, 1, phi 1, 1, and I would have phi 2 2, sorry, phi 2 2 and phi 1 3. So that's exactly the same as this one. Okay, so we didn't generate any new terms by the second part of this permanent. Let me do this one now. This is going to be phi 2 1. Okay, so that's going to be phi 2 1. And it's easy to see what will happen afterwards. It's going to be phi 1 2, phi 1 3, and that you're going to get that once more. Okay, so these two terms are going to be the same, because if I exchange between these, I'm not generating a new term. Okay, so this is what the permanent gives you, and that's six terms, okay, n factorial terms, but only n factorial over n 1 factorial, etc., are distinct, right? So in this case, it means 6 factorial divided by 3 apologies, 3 factorial divided by 2 factorial and 1 factorial are distinct. So there are three distinct terms in in the permanent when you write it in terms of the permanent. Okay, so this actually relates the when you have all the configurations versus only the distinct configurations. But I want to just emphasize that the wave function, so I'll write that again. So I'm going to sometimes write psi wave function. Okay, so one, it has n particles, and it, in general, a bosonic wave function. Sorry, apology. You know what? I can fix that. And 1 and 2, etc. factorial divided by n factorial square root sum over p. And let me just simplify notation here. So here you would have phi 1 p1, phi 1 pn1. So there have to be n1 terms multiplying here, okay? And then you keep going with n2 terms and so forth. Okay, and this is a bosonic wave function. And the cat notation for this wave function is going to work like this: n1, n2, n3, etc. Okay, so what we mean here is that we have a wave function in which of bosons in which n1 particles are in state 1, n2 in state 2, n3 in state 3, and so forth. And we're just always going to say that we have n particles in our system. Okay, and now I have a little bit of time, so I'm going to work out the normalization. Okay, so that's not a hard exercise given what we have seen above. Okay, so this has to normalize to 1, but I just want to emphasize that if I take an n particle integral, okay, and I put here my wave function and square it, this of course is the same as n1, n2, n1, this particular scalar product, so scalar product of the vector with itself. Okay, and what do we have here? Well, first of all, we have to square the combinatorial part. That's that square root. Okay, so that becomes n1 factorial, n2 factorial, etc., divided by n factorial, and that's squared. Okay, but we also have the many particle integral to deal with. So let's deal with the many particle integral. We have d1. So there's this is a multiplication that starts here and continues here. dn. Sorry. Okay, and what do I have here? I'm going to have here the square of the sum over distinct permutations. P, phi 1, p1. Sorry. Let me fix this. P1 phi 1, p and 1. And there are n1 terms here, n1 terms here. Let me explain a little bit. Okay, you know what? I finished this expression. So I have also n2. So this continues, okay? And I also have to asterisk this because we are squaring the wave function. And here I have another sum, which is also the distinct permutations, p prime 1, but they're also distinct from the ones above. They're the same set of permutations, okay, but it's a different sum, so I need a different index. And here again, I have n1 terms multiplying, and then I have n2 and so forth. Because I close this, and that's what we have. Okay, and now we have already seen, okay, that since this is a sum over distinct permutations, let's recall what happened in the three-particle problem, right? So if we go back to the three-particle example, and when we did the normalization of the three-particle example, we saw, so we took distinct permutations, right? We took distinct permutations, and we saw that what happens if the permutations are like permutations, right? So we here what we did is we also squared all the permutations we have, and we actually then considered the terms which are like permutations. That was this calculation here, okay? Remember that we were working out the normalization, okay? So this is there's a little mistake. Well, it's an inconvenience, let's say, in the notation, that for the normalization I used the letter n, which is also particle number. Apologies for that, but here I meant normalization. So here I already put a normalization. But the point is that what did we do here? We calculated the like terms when we did this integral, and the like terms are, so this is a like term, because we have the same permutation on the asterisk side and the non-asterisk side, and that gave us a 1. Okay, that gave us a 1. When we did the unlike terms, for example, we did this particular permutation with this one, we got a 0. Okay, and I'll just state without proof, although I think it's pretty obvious, that the same thing happens in the many particle case. Okay, so if I go down where I was, the point is that when you do this integral, the like terms will give you 1, okay, and the cross terms will give you 0, because these are distinct permutations, okay. And you know how many, I mean, okay, this p sum over p, of course, is exactly this many terms, okay. So this is actually the normalization, which has to give you 1. Let me just do that step by step. Okay, so again, here's my n1 factorial, n2 factorial, etc., divided by n factorial. And I'm going to now use the fact, so let me write my integrals here, d1, dn, that I don't need two sums anymore, because we determined that the cross terms integrate to 0. Okay, so what you're going to have here, you could write the sum out here, okay, and what you're going to have here is phi 1 p1 star phi 1 p and 1 star, okay, and there are n1 terms like this, okay, and then you're going to have this for phi 2 as well, okay, but you're also going to have the same term again, but not asterisked. So p1 p and 1, and the same, and this keeps going. Okay, so there will be here there are n2 terms. Okay, so this line is multiplying this line and it's being integrated over. Okay, and we don't have to know the permutations, but we know that, well, in a particular member of the sum in which the number 1, coordinate 1, falls among these, among the phi ones, it's going to fall among the phi ones in both places because it's the same permutation. So in other words, this integral will just give you 1, but it's how many times will it give you 1? This sum will have exactly n factorial over n1 factorial, n2 factorial, etc. terms in it. So this will integrate to be 1. Okay, so let me just say that this is the we just verified the normalization in this calculation. Okay, so thank you very much for your attention.